5A forces. 5.1 Forces weren't always with us. Captain, the ship's shields are down to less than 50%. We'll never hold off the next attack. Entertaining science fiction stories of improbable futures and pasts have made much use of the basic principles of immense forces and force fields. However, the real world of forces is no less fascinating. In ancient Greece, Aristotle believed that all matter possessed an urge to move in certain ways. Matter naturally moved up or down, depending on its nature. Once things were set in motion, their natural inclination took over and guided their behavior. He believed that all the natural changes of motion came from within material things. During the 3rd century BC, Archimedes, a Greek mathematician, engineer, and astronomer, was the first to write about the causes of motion. About 1800 years later, Galileo realized, in a moment of inspiration, that the motions of objects change because of a push or a pull on them, not because of some impulse from within themselves. Isaac Newton was born around the time Galileo died. He called Galileo's pushes and pulls forces. He also developed mathematical equations describing how forces affect motion. Perhaps his most important contribution to science was his description of the gravitational force, which explained why the moon and planets stayed in their orbits. In the 1700s, the British physicist Henry Cavendish, 1731-1810, performed an experiment that allowed later scientists to calculate the gravitational forces between objects. Since the early 1800s, physicists have devoted much effort to developing models to describe all the forces they observe in nature. Scientists aren't entirely sure what ultimately causes forces, though they have developed complex models that work for this purpose. They have described how forces cause phenomena in nature through dynamics. Some of the most important aspects of dynamics are identifying the kinds of forces, explaining how forces interact with matter, and describing how they affect the motions of objects. In this section, you will learn about the different kinds of forces that are found in nature. 5.2 Classifying forces. A force is a push or a pull on a system. This description fits well with your experience and observations of forces in nature. You've probably pushed a grocery cart or pulled on the leash of an ornery pet. You know that powerful engines push rockets into space and that cables pull elevators upward. When a force acts on a system, it pushes or pulls, at least at any given moment in a single direction and with a certain magnitude. So, forces are vectors. Sketches that show how forces act on systems are force diagrams. These use an arrow to show which object a force acts on, how large the force is, and the direction of the pull or push on the object. See Figure 5-3. We can classify forces in our everyday experience into two broad categories: contact forces and field forces. Physicists believe that they are the visible results of four fundamental forces that are present in all matter. See the facet below. Let's take a closer look at these two kinds of forces. Contact forces, and as their name implies, contact forces act only when one system touches another. Contact forces originate at the atomic level of matter. Atoms resist the intrusion of other particles into their space. So when the atoms of another object push on them, they push back. You exert a contact force when you open a drawer, step on the pavement, open a jar, or apply a strip of adhesive tape. Scientists and engineers properly call contact forces mechanical forces. These include compression, which pushes things together, tension, which pulls things apart, torsion, which twists objects, and shear, which can cause one part of a material to distort or move parallel to the direction of the force relative to other parts. Field forces. Forces also act between objects that are not touching. Though such forces originate in matter, they do not need to act through matter. Long ago, people observing pushes and pulls between objects that weren't touching considered such phenomena abnormal, even magical. Newton called them action at a distance forces. Today, physicists explain that such forces act through a force field. So what is a field? In physics, a field is a volume of space in which every point can have a different value of a dimension of interest. For instance, Imagine a room with a fireplace containing a roaring fire. Nearer the fire, the temperature's higher. Farther away, the temperature's cooler. Every point in the room, ceiling to floor, has its own temperature value. This model of the room's temperature is a temperature field, an object surrounded by a space in which every point can exert a push or pull produces a field force. In other words, each point in the field has a force vector associated with it. Field forces produced by matter affect susceptible objects by attracting or repelling matter. The principal field forces are the gravitational, magnetic, and electric fields. A gravitational field surrounds anything made of matter, although only planet-sized masses or larger exert significant gravitational force. Gravity affects everything, including light. The sources of magnetic fields are magnets and moving electrical charges. Magnetic fields affect susceptible materials such as iron, magnets, or moving charges. Electric fields surround and affect electrical charges. All fields extend outward from their sources without limit, but their influence weakens rapidly with distance. See Figure 5.5. 5.3. Balanced and unbalanced forces. Every object in the universe has more than one force acting on it. For example, the forces acting on an airliner flying at 10,000 FFT include the thrust of its engines, the lift on its wings, air resistance, and, of course, Earth's gravity. So, if forces like these are acting on each object all the time, why isn't everything in continual motion? It's because most objects experience balanced forces, multiple, simultaneous forces, whose pushes and pulls cancel each other out. Let's look at a simple example of this. Assume that two groups of students are pulling on a tug-of-war rope, as in Figure 5-7. The external forces that the teams apply, acting on the rope system, come from outside the system's boundary. If the teams pull equally hard in opposite directions, the two forces are balanced, and the rope doesn't move. As far as the rope is concerned, there is no net force acting on it. The rope system acts as though there were no forces applied to it at all. On the other hand, if one team pulls harder than the other does, then an unbalanced force acts on the rope. The net force equals the difference of the two forces. The net force acts in the direction of the larger force. The stronger team will eventually drag the other team over the line in the direction of their pull. In the real world, there are usually more than two forces acting on a system, often in multiple directions. If these forces cancel each other out, they are balanced and no net force exists. If they don't cancel, there is a single net force exerted in a specific direction. The result of an unbalanced force on a system is a change in motion. This will be the topic of Section 5B.